last one.
Lembarti ma'am.
Start until
15 minutes.
start.
Can you start? Otherwise, if you just miss the concept, then it's going to be very difficult for you to catch it up later. Because the time is very short and there are so many things which we have to learn. And in case if you miss the concept, then it's going to be very difficult to implement it. And let me clear you one thing. I tell you this code. Okay, what is this program? I will run in front of you. The rest of the programs you need to exercise by yourself. You are going to face number of errors, problems. Just Google it, just observe it, and then just try to execute it. Okay? So that way you will learn a lot. So in this session, now just forget your system. Just see here. When I tell you that you need to write this program, only then you should have your system in front of you. Now you can turn your chair. Have a comfortable position. No need to look into the system for now.
Kindly write the number which you are using nearby your name. Okay. All of you can sign in.
So let us start the things now. So this has been the history of the development of foreign supercomputer. So it all started in 1991, and now recently we can find number of HPC systems named as Param Shower, and it has been distributed to many IITs, NITs. So more or less, if you have come across any HPC machine in any NIT, then more or less that is going to be Param Shower only. So a customized version have been sold to many NITs and IITs. So I know IIT Mandi is using one such, then NIT Allahabad is using another, one NIT So this is what we are using, Param Shower. Okay, and at the core, the CDEC people are using Param Utkarsh, AI Siddhi, then Param Eravat they are building. So these are some of the names of HPC systems, and that has been the evolution of HPC. Now, in continuation of our session 1 discussion, again you can see the same architecture, but this time the architecture has been presented in the terms of nodes only. And in this diagram, the nodes have been divided into two categories. The first one is compute nodes and the other one is login nodes. So let me be very clear, all the nodes are equally capable of doing the computation. They have just given the responsibility of playing the role of login nodes. It is not like they are not having the capability. Rather, they are using their capability to handle all the login formalities. Okay. So we have got number of nodes, and of course they are interconnected. It depends upon the application and the program how we are making the use of these nodes collectively. Fine. Now, let's say we have got a node, and in that node we may have number of sockets, right? So in this case we have got 2 sockets, and then in each and every socket we are going to have number of cores. So by now you would have run that command CPU, ls CPU, and you would have observed the things which we are presenting in the slide, right? Now what these nodes are going to do, they are going to share the memory system. So you would have observed somewhere, right? Now the problem is how efficiently we are going to make the use of these cores. So let us see, we can do that with the help of OpenMP. So when we talk about having a shared memory module, okay, when the memory is being shared, in that case we are going to have the framework of OpenMP, and when each and every processor have got their own memory and they collectively over a network is going to make the use of that, then that is the case of NUMA. So that is another way, and in that case we are going to make the use of MPI. Okay.
How do we know whether the memory is shared or distributed from this configuration repository?
In this,
Yeah. How do I know whether it's using a shared memory or a distributed memory?
you can see anywhere in node 0, anywhere in node 1. And in each and every HPC system, it is very much obvious. Why obvious? Because if you see carefully, since we have got number of nodes, that means of course they are going to have the NUMA system. If only a single system is there, only a single processor is there, and in a single processor number of CPUs are there, then that is going to be a case of UMA. We saw that diagram in the first session, right? Now, what is OpenEP? OpenEP is a portable shared memory programming. It is easy to learn, and parallelization is fully controllable. Is fully controlled by programmer. So we have program directives for Fortran and trademarks for C and C++, and recently even the Python is also being supported. Then we have got runtime, number of library routines, environment variables. So these are the functions which will help you out to create the parallel environment. Now, this is how the thing happens in the background. So, OpenMPI generally follows the fork and join programming model. So, it all starts with a master thread, and that's where the parallel region gets started. It forks number of threads, and a parallel region is being created. And when the job is done, again we are left with the master thread only, right? And when the need arises, again a parallel region is being created by forking the threads. And at the end again, the join operation is being done, and the other created threads are being suspended, and the control is being handed over to the master at last. So you can visualize this diagram. Let's say you have got a big program, and in that big program, this much portion can be run in parallel. So that's where you have created number of parallel threads, and this is the synchronization phase, where some shared variable came across, and then you have killed all the parallel threads, and you did this synchronization. Then later part of time, when this situation again arises, again you have created number of parallel threads. Okay, so this process will go on. Is that clear? So this is called as fork join programming model. In threads, generally the threads are being numbered from 0 to n-1, where n is the number of threads, and then we have got OMP underscore get underscore num underscore thread. This is the variable which is going to give you the number of available threads in your system. We have got the processor, we have got CPUs. Now, given the infrastructure, given the hardware, how many threads we can create or how many threads we can use? Each and every system have got their own ability, right? So as per their ability only we can create the number of threads. So this particular variable is going to give you the number of available threads. How many threads are available for you to use? Okay, so it may vary system to system. If I run it in my system, then it will be different. If you run it, then it will be different. Okay. Then OMP get thread num tells the thread its number. What is the number of that thread? That is going to be held by the second parameter. Then a simple program with several threads is able to handle several tasks concurrently. Fine. Okay. Each thread is going to have its own stack at register. Okay. So each thread is going to have their own local memory with stack and register. Thereafter, again, now we are having the same thing in the form of an execution model. So let's see, we have got a parallel program. So it all starts with your main function, right? So at that time we will be having only one thread, and that is your master thread. Then you are going to define the parallel region with this hash fragment. So this directive is going to tell the compiler that you need to create multiple threads for this particular section. I want to execute this section in parallel. And how you have told this to the compiler? By using this hash pragma directive. This is again your simple C program. The only difference is now you have stated that this has to be my parallel region and this region has to be executed in parallel. Fine. Then again that parallel region has ended, and it is very much possible that some point of time again you need to create the parallel region. Okay. So the visualization is initially you will be having a master thread. The moment you have defined the hash pragma on parallel, number of parallel threads are going to be created. How many threads? It depends upon your implementation and your hardware specification. And again, when the directory is defined, again a parallel region will get created.
So we explicit code for synchronization, because after the parallel synchronizing, don't we need to specify?
Within parallel region or within the parallel code, you can have the provision of synchronization. That's where that critical section will come into picture. How you are taking care of critical section. Okay, that is nothing but the way of synchronizing as well. Then there will come some concepts of barrier as well. Okay, where you say that if some of the threads are stopped working, even though you need to exit the parallel region. So there are a few things, a few mechanisms to synchronize the program. So critical section is the most famous one. So far, the thing is clear. How do we create parallel region? Okay. Now let us see how our program look like if we talk about the serial program. So this is the basic syntax, right? We use the header files, then we have the main function, thereafter we use the printf function to print the text, right? And how do we execute it? With the help of a GCC compiler. We said what compiler we are using, then what is the name of the C program, then what is the object file. We give the name of the object file. So this is how we execute a simple C program. So your first task is to write a basic hello world C program and execute it in Linux environment. Okay, so that you get comfortable. Okay, this is how we need to execute the things. Okay, so the first thing which we need to do. Is it clear? Yes. Can I move forward? All? Now, hash pragma omp is a set of directives used in OpenMP, that is Open Multiprocessing, for parallel programming in shared memory system. Then the hash pragma omp directives are used to instruct the compiler to parallelize the certain section of code, distribute work among threads, synchronize threads, and control other aspects of parallel execution. So this is what we have just discussed. The moment you write the hash pragma omp, that means you are instructing the compiler to parallelize that certain piece of code, right? So this was the execution flow of a serial program, and now this is the parallel program for the same hello world. So what changes we have done have been indicated in the directory. So you have included one more header file, right? Then you have specified hash pragma omp parallel. So what it will do the moment you specify this particular directive, it is going to create multiple threads. How many threads? Whichever are available as per the hardware specification. Okay, so those many threads will be created in parallel, and all threads will be executing this printf function.
So will it not be a wastage of CPU cycles?
We are just seeing how we can make the use of this. We are just learning how to use it. Okay. Our motto is not that just print hello home 16 number of times or 16 number of times. We are just trying to see that how exactly these things are working. Okay, we are trying to understand their working mechanism. Is that clear? So it is requested to please note down this program because you need to exercise it. Just the right one you can. It is first program you should write. Then rest of the programs you can take this name. So that you can, because you need to write in the system as well, right? So that way you will have the practice of syntax. It is first program. When three program comes, then you can take the details. Write in copy again later. You can write in system. Whatever is the fastest way of noting, except clicking a photo.
In which screen we have typed up this filter?
Well, you copy, you just first write it.
I ready.
Now the moment we are done with this program, so this is how we need to execute this program. Now again you must have to notice this red portion. So this is a switch which needs to be specified whenever you are compiling any parallel program. Okay, so you need to specify a openmp after the compiler name, then the C file, object file. Okay, and then please pay attention. Export omp num thread equals to 2. That means this is the environment variable omp underscore num underscore thread equals to 2. So this is the way to specify that at max 2 number of threads you will be using. You may have 40 threads or 400 threads, but how many threads you want to utilize? Only 2. So that can be specified using the environment variable. Okay, so that you need to export. And then whatever object file has been created, that you can execute. Okay, dot backslash and the name of the object file. If you are given the name, otherwise dot slash a is the default object file. Then this is going to be your output. If all have noted, please let me know. I'll move forward. Please take your time and understand this piece of code, because slide after slide, then the concept will get complicated. especially that execution part. Okay, what is the command to execute? How you are setting the environment. Okay, how you compile, how you execute.
That web portion export, does it come automatically saying that there are 2 number of threads, or do we have to
Specify.
Make it
Specify.
code and we have to see how to spell it.
If you want to have 3, you can give 3.
That we may have number of threads. We may have 100, 400, but if we just want to make use of 2 threads only, so that we can specify. Out of all the available threads, we only need to use 2 threads only. Then all. Then because back to back we have got tomorrow, I guess you have got MPI session, then it is going to be very hard for you. You don't understand how these things are being handled. Done? Okay. Now, this is how the flow is going to be. If you try to visualize how a thread is being created, initially that is master thread, and the moment you have specified a parallel region using hash pragma om parallel. Since you have specified 2 threads using environment variables, in that case, how many threads are going to be created? 2. Now, there is a quiz. The question is, which preprocessor directive is used to control compiler optimization settings and other implementation specific features? Very simple one. Just read the answers, read the options, and you know the answers, right? Okay. So the answer is? The question itself tells the answer. Now, you need to write an OpenMP program such that it should add your favorite number, for example 5, to the thread ID and print the result along with the thread. Now you can take its photo. First program you should write, then you should write this program. You have got 15 minutes in total. I won't help you in debugging. Now the only thing is how you get a thread ID. So the variable is open underscore get underscore thread underscore num. Thread. Okay. So that's the function. Now you need to use the editor.
Yesterday's sir showed
Editor, you can use VI editor, you can use Nano editor, you can use Vim editor.
Yesterday sir showed us. You are inside.
Excuse me. You are there already?
Connection is about
Connections
login
again. You can use any editor, for example, VI editor, Vim editor.
Yes, sir. connected to the HPC system. Connect SRM
I'll
HPC
tell you
connect
the first program. I'll show you. Okay, can you see the screen? All. So I have opened my Linux system into it. I have created a subsystem. So as you can see, I have got 16 CPUs and 8 makes I can create 16 threads. What you can do to write a program, you can write Vim. This is the name of the editor, okay, and then the name of the program. For example,
stop as usual.
you can use here. Vim will work. You can write here.
Session
Can you see that?
103.4.
Vim, then the name of the program. All of you, please see carefully so that you can understand.
SRM labs.
We need to synchronize, right?
Number now 06
All of you, please see. What I have done, I have just used Vim editor and I have written the name of a program which I am writing. Enter. Okay. Now you are in escape mode as of now. So what you need to do, you need to press insert button. Okay. Now you have got writing permissions. Now you can write the program.
File name. Dot. File name dot. sh. Vim space. File name.
To define number of threads, right? So if we have defined that only 2 threads should be used, in that way we will be having the execution by 2 threads only. So that we have already executed. Now this is another way of doing it. In this case, what we have done, we have made the use of this function to set the number of threads. one way is the default one, other way is where you are exporting number of threads, and this is the third way. If you have set the environment variable and thereafter you have written a program like this, then this will have the priority. If you have defined the environment variables where you have set the number of threads as 2, and in the program you have written this function and you have mentioned 4, then 4 threads will be there for the execution. Okay, so this is another way of doing it. Is that clear? You can take this snap. Any one of you can take a snap, so that after the lecture you can practice these things. Is that clear? Yes, yes. In the program itself, we are defining the number of threads which are going to be available for us for the execution. Okay. Just see the execution. Okay, you will realize what will come. So after 24, again the 6 more threads are going to do the job, but those threads are going to be the earlier one only. Okay. Now, as I told you, routines have higher priority than the environment variables. So whatever number of threads we have set inside the program using these particular functions is going to hold the priority. Now, the second question, how many threads are created by default when you use #pragma-omp_ll? The answer is by default the number of threads created by #pragma-omp_ll is determined by the environment or can be specified using environment variables. Now, just see carefully this program. What is happening in this program? We are getting first thread numbers, then get number of threads. How many threads are available for us? Then what we are doing? We are printing that which current thread is working out of how many threads. So the output will be like this. Okay, so one function is giving you which is get number of threads. There is a difference. This will give you the thread number and this will give you total number of threads. You have already made use of this, right? After taking the numbers, you are storing it in integer variables. That are the straightforward thing. The point is, we have these two things. Things like this, we do have. And when we have those, when you define this header files, and when you use this spread path. Okay? Is that clear? Now, write a program such that it should add the thread IDs of each thread and print this up. Take this line. I give some hint as well. So this is how this program is going to be. So first, it is expected that you are going to make it by your own. In case you fail to do so, then you can refer it. Okay? So the point is, you are creating an array. Initializing that array. Thereafter, you are getting the thread ID. And then in the array, all the thread IDs are being stored. Okay, so a parallel region will be created, and whenever each and every thread gets created, it is going to store its ID into that array index. So if you have created 8 threads using the parallel region, please keep silence. So if 8 threads are there, so let's say thread 0. So it is going to be the 0th element of the array, and its associated thread index is going to be stored in it. So if you have created parallel region and 8 threads have been created, so they are going to store their respective values, and then you will be having all those values in this array which you have defined earlier, right? And then thereafter what you are doing, you are taking the help of a for loop to find out the sum, right? And then you are printing it. Okay? So just take a photo and have it as an assignment. Clear? Should I proceed? Should we proceed now? Now, just keep clicking photos, huh? You will get one by one so many programs. This time write an open API program such that it should print the sum of square of thread IDs. Also make sure that each thread should print the square value of their thread ID. Straightforward. Whatever thread number you are getting, just multiply it by itself and then print it. Right? Take the photo and thereafter you need to make it. Done? Now we are going to see the module 3, which is scope of data variables. So since we are working on parallel region and number of threads are going to use the shared variables, so how we are going to set the scope of data variables, that is very important to learn. So to begin with, we have got variety of ways through which we can set the scope of data variables. So this is the default one. So let's say we have got a variable, integer variable, initially n equals to 2, and we have got a single master thread, means a simple program. Thereafter what we have done, we have created the parallel region, hash pragma on parallel, and then number of threads have been created in parallel, right? So what will happen by default, we are thinking that each and every thread is going to have this shared variable. So if we have created 4 threads, then each and every thread is going to share this variable. This is the default one. So let us try to understand this one. Is that clear? So let us try to understand that concept with the help of this program. So again, header files have been given, okay, main function has been written, thereafter 2 integer variables have been taken, thread ID and sum. Then we are starting the parallel region by using hash pragma on parallel. Then what is happening? We are getting the thread ID using the function on get thread number. Okay, so thread number we have got, fine. Then we are calculating the sum and sum plus TID. So whatever is the value of sum, in that value thread ID value will be added. if we have created 5 threads indexing from 0 to 4, then these should result 5 plus 0, 5 plus 1, 5 plus 2, 5 plus 3. Okay, just try to visualize the moment you have written parallel, number of threads is going to be spawned and all of them together will be doing this thing. But the problem is this is a shared variable. That means all are going to access this variable. That means
assignment we should have done in this way, right? Rather than creating an array and storing the ID and adding up that.
just see it, run it, you will get to know. But in the last one, that rest condition is not there. But in this one, we are going to have that.
Someone to do the sharing.
So what we follow this program? What is happening over here? 5 parallel. We are just assuming the 5 threads are there. They will be created in parallel and they will be executing this thing. So now, thereafter, after this parallel region, what we are printing? We are printing again the thread ID. We are printing the thread number and the value of sum. Okay. So let us see what we are expecting. So this is what we are expecting. If 4 threads are being created, then each and every thread should add its index value. Thread ID value 0, 1, 2, 3. What is the initial value of sum? 5. So when thread 1 is going to execute, it should be 5 plus 0. When first thread ID is executing, that it should be 5 plus 1, then 5 plus 2, 5 plus 3, and the last printf statement should be this one, right? Which is giving you the thread number and the value of sum. So now let us see what is the value. This is what we were expecting. And this is what we got actually. Why it's happening? Because of shared variable. All the threads are accessing that value of shared variable simultaneously. And the moment it is done by one of the threads, another thread is coming and changing its value. We are not controlling the shared memory space or shared data variable. That's why this behavior is coming. Okay, by the time the other thread is putting its value, some other threads have read that value. So conflict is being done. So that's why this behavior is being reported. Okay. So what is the problem? Problem is race condition. Each and every thread is trying to access that critical section, which is that shared variable sum. Because a parallel region will be created and that is shared variable, so each and every thread is trying to get the access and doing the modification. That is the problem. Okay. So learning, we need to be careful while declaring the scope of variables, the variables which is going to update in parallel region. So in the first session, we told that how we should write a code. So we should take care of these things, which is the shared variable. And then you have to tackle it accordingly. Okay, there are variety of ways. So this is one problem which you need to take care of. The variables which is going to update in parallel region should give special attention while writing a parallel program in shared memory system. Now, there is a question: what is a shared variable in OpenMP? Give me the answer.
B. A variable accent.
B. Confirm?
Yes.
लॉक कर दे.
Yes.
Congratulations, you got one. Okay. Now, what about this one? Again, option B.
No. You cannot avoid. That word day. Maximum parallelism across.
First.
Efficient use of B category. Maximum parallelism across threads. Is
How many A? How many B?
B.
How many C?
D.
D. This time the options are distributed. I won't have much loss. Okay. The correct option is B. We need to ensure that we avoid data resistant information issues while dealing with shared variable. Now, what can be the solution of this problem? So, the solution is we can make data variables private. Okay, so the moment you make data variables private, each and every thread is going to have their own local copy of the variable. That means they do not need to fight with the other threads. Okay, so that is the first solution. Clear? So as you can see, initially what was the variable? Guys, you can go outside if you need to talk. Okay, your teachers are trying their level best. So initially, what is the value of the variable? N2. The moment you define it as a private, so the value is going to be either undefined or 0 upon entry and exit of parallel region. That means you can see now each and every thread is going to have the value of n as 0. The moment you define it as a private. Okay. So immaterial, whatever was the value earlier, the moment you define it private, it will be either undefined or 0. So the question is fill in the blank. This time you must have to notice that we have added one more clause.
Private.
Okay. What is the variable which you do not want to share with the other threads?
Sum.
Okay. So this is how it is going. You can have a click of this and practice it. Just take the photo. But immediately after this session, you will need to practice, right? Clear? So, what is the output of the program? Because each and every thread is going to be 0. That's why. Right? That's why we are getting these values. Still the problem has not been solved. But now we are able to observe the difference which was there in the earlier output. Right? Now that was the earlier one and this is the current one. Isn't it? Is it clear? Now this has been learning, okay, we have discussed. This is the other assignment which we need to write, okay, where you need to create a variable Aryabhatta and declare it as 10. Then you need to write an open MPI program which should print the result of multiplication of thread ID and the value of the above variable, which is 0, which is 10. Okay. So in this case, you need to declare the variable R beta as private. Now, this is another scope of data variable called as first private. Now, just try to see the difference. This time, what's happening? Whatever was the value of the variable, that is being copied to each and every thing. This time, it is not initialized to 0. Rather, it has got the initial value. Okay. And now, if you include first private, earlier it was only private. Now we have got first private. Okay. For which variable? Sum. Okay. Now let us see what is the output. Now this is what we wanted initially. Remember that program? Now we will get it out. Okay. So I hope you would have understood this flow of program. Okay. Now, what happens if a variable declared with first private is modified inside a parallel region? Give me the answer. We have copied it, but each and every thread has got its own stack and memory. So whatever changes will be there, they will be kept to that thread only. Okay. Second one. The answer for that is going to be the last one. Okay. Now, this is one more type which is called as last private. We have seen private, then we have seen first private, now we are seeing last private. So, whichever thread is executing the last iteration is going to give that value. For example, 4 threads concurrently have been created, and whichever thread is executing the last iteration, that value will be written by this last thread. Let's say we have got 10 iterations, okay, and 10 threads. So whichever thread is being executed at last. Some thread may finish their job early, some may finish their job late. Okay, let's say at last thread number 2 has finished. So what is the value of that thread 2? That is going to be written by this last thread.
So every thread are going to perform the same task. Then why is that difference you are going to come
Yes, because the moment you have got number of iterations, it is not necessary that each and every thread is going to have the same job. It is not necessary. Okay, you may come across sections where you are dividing the threads across sections of loops where different conditions are there. So number of possibilities are going to be there. So
In
far
our
you have
example,
just,
the previous thing,
so
the
far
addition only are doing.
Yes,
In all
so
the
far-
threads, the same thing we are doing.
yes, so far you have seen the straightforward things. So far you have seen the straightforward things. Okay, but some other things will also be there, where in some iteration it is going to take some time. Okay, not because that they are accessing the shared variable or some critical section, even some other reasons may be there. Just think of a program for loop where for a particular iteration you have done some more if comparison. If I equals to 0, then do this. If not, then do this. Same in the for loop. Right? Is it clear? Now in this case, what is happening? We are printing the value of the last iteration. Okay, so you can just take the snap of this, and whatever will be the value of the last iteration, that is going to be printed. Okay. So these are the changes. So again, you have created a parallel region. You have had 4 loops, so 10 iterations over there. So 10 threads will be created, and then they will be executing this thing. And whichever thread is executing this one as last, that will be printed over here.
So, if I didn't give last private, just private I've given, what will happen?
That case we have already discussed. In this case, each and every variable will be having 0. Okay, so it is immaterial that what value they are carrying at the last, because both have got different purposes. Okay. So this is the value in the first term. It is having the default value, but for the rest of the threads, we can observe the values. Okay. So final total 9. So that is the value which is being given by the last thread. This thing, that is the default value which is coming. That you need to understand. So the last thread have carried this thread, which is been reported at last. Okay. Now, this is a good program, so it is going to give you a lot of insight. You can have a peek. So in this program, what we need to do, we need to write an open MPR program that calculates the sum of first 20 natural numbers with parallelism. Each thread should compute a portion of sum by iterating through a loop. Implement the program using the last private clause to ensure that the final total sum is correctly computed and printed outside the parallel region. You can just skip this portion. Okay, this is a bit ambiguous, but the rest of the program you can execute. Okay. Now, module 4 work sharing with loops. Let's actually come to the point. So these are the work sharing mechanism, also called as scheduling mechanism. So far we have seen how exactly we can distribute the work, or how exactly we can create the parallel section, right? Now we have got certain types of scheduling called as named as static, dynamic, guided, and runtime. So let us see them with an example so that we can understand. Static without chunk size, static with chunk size. Okay, fine. Now, this is how we can schedule that how many threads are going to execute how many number of iterations. Let's just imagine we have got a for loop where 1 million iterations are there, or 1000 iterations are there, and we have got 100 threads. So how we are dividing that workload among the available threads? Okay. So just see this program. What is happening? We are defining chunk size as 1, then we are defining n as 4. Basic program is there, basic main function is there. Then we have taken float arrays ABC. Then we have initialized them, right? Thereafter, we are creating a parallel section as pragma om parallel private, and we are keeping private 2 variables, that is I and thread ID. Thereafter, we are getting thread ID, and we are getting the number of threads and printing them by checking this condition. Thereafter, the main work is happening over here. Okay. Okay, so again we have created a parallel region, and in this case we are using static as a scheduling schedule mechanism with a chunk size of 1. Chunk is equal to chunk size, and what we have defined it as a 1. Okay, so now the problem is we are going to run it up to 4. N is 4. What is the schedule mechanism? Static. Okay. Now let us see the output. Okay. Printf, thread ID, then the index and the value of CI. How many number of iterations are there? 4. What is the chunk size? 1. And what are the number of threads? 4. So just try to observe this out. How many threads are there? 4. And what is the chunk size? 1. Chunk size means whatever number of iterations we were supposed to execute, one thread means how many iterations one thread should execute. If the chunk size is 1, that means 1 iteration is going to be executed by 1. If it is 2, that means 2 iterations are going to be executed by 1 thread. If it is 3, then 3 iterations, and so on and so forth. Okay. So in this case, since the iteration are 4 and the chunk size is 1, and we have got 4 available threads, so each and every thread will get the opportunity to get executed. If we have got 4 threads and each and every thread has 1 iteration to execute. How? Because chunk size is 1, which is going to tell a thread that these many iterations you need to execute. Now, what will happen in this case? This time the chunk size is 2. So that means thread 0 need to execute 2 iterations. And how many total number of iterations we have got? 4. So 2 are done already. Then thread 1 will get the opportunity to execute the rest of the 2 iterations. Okay. So this is how this static scheduling is going to be executed. This time chunk size is 4, and we have got total number of iterations 4 as well. So only 0th thread will execute all the 4 threads. Is that clear? Now since the chunk size is 2, so each and every thread will be getting 2 iterations to execute, right? Since this time we have got more number of iterations, so that way it has been accommodated. Okay? Is it clear? Now we have got the next scheduling mechanism, that is dynamic. Let's say we have got 110 number of iterations, okay, and we have got 5 threads to execute them. So in dynamic scheduling, what will happen if we have the chunk size of 20 iterations? Then in dynamic scheduling, the first 100 iterations will be first divided equally, because we have defined the chunk size as 20. So each and every thread will be executing 20 iterations. So all 100 iterations are done. How many left? 10. How many threads we have got? 5. Now all the number of iterations will be divided by the number of threads. So each will be having 2 iterations to execute. This process or this process is called as a dynamic scheduling. Okay, larger is the grain size, larger is the way of having parallelism. Then whatever iterations are left, that are going to be scaled accordingly. Okay, is that clear? So in general, that is what we do in dynamic scheduling.
Sir, I'm not able to understand. Can you repeat again?
Yeah, sure. So the problem was, what if we have got 110 iterations to execute, and how many number of threads we have got? 5. So in dynamic scheduling, what we can do, or what generally happens, if we keep the chunk size as 20, then what will happen? Each thread will be having 20 iterations. We have got 110 in total. So first we are dealing 100 iterations. Okay. So 20 iterations are going to be executed by, why? Because the chunk size has been declared as 20. 100 iterations have been executed. Now the problem is to execute the remaining 10. Now since we have divided that chunk size as 20, and this is which one? Dynamic. If it has been the case of static scheduling, then the thread 0 and thread 1 will be executing the thing. If the chunk size is 20, then only thread 0 will execute. Okay. In dynamic, it will again distribute what is the available iterations that need to be executed and how many threads we have got. If all 5 are available, then it will divide it in the 5. Let's say one got engaged. One got engaged and now only 4 are available. Then it will be divided in 4 only. If 3 are available, then it will be divided in 3 only. Like.
In the case of static, if there is a 10 jobs, 10 iterations are remaining, it will be allocated, all the 10 will be allocated to one thread. Here, this will be distributed. So what is the advantage of this?
Advantage, because in the larger picture, the overhead and CPU utilization, unnecessary you are giving a thread to job where it is not, and the other threads are sitting idle. So that is the case. So rather than discussing this theory directly, I told you how to implement it, or how exactly it is being implemented. So this time, thus the change is going to be dynamic.
What happens if a thread remains idle for a long time?
Please come again.
What happens if a thread remains idle for a long time?
Efficiency.
That is up to the programmer. Why the programmer is giving the chance to a thread to. Okay. So you have to try your level best so that all the things.
Efficient utilization of resources.
So accidentally she missed that hash pragma. Only one is being executed. Right. So that is our problem. Why we are not exploiting the whole resources. Okay. So this is the case, although we have already discussed. So then guided runtime. In runtime, you export this environment variable where you define what is going to be the scheduling strategy and what is going to be chunk size. Okay. Now the next module is work sharing, and that can be done using sections. So in this case, you can identify the section of the code, and that can be written in the section, and all those sections can be executed in parallel. Okay, that you can identify. So again, you need to SID, you need to identify that region. And then you can put it into the section like this. So in this case, what will happen? Number of threads are going to be created. In this case, how many? 3. And this will be taken care by thread 0, thread 1 and thread 2. So 3 parallel threads are going to be created and they will take these jobs respectively in parallel. Okay, so here you have defined them in sections. Is that clear? Then so 2 different sections will be defined for that. Now we have got next module, that is synchronization, which is quite important, and it is going to let us know the mechanism through which we can handle the rest conditions. Okay. So just see this program and what should be the output of this program. We have got an array. Array is being initialized. Fine. And what is the size? 10. Then we are trying to calculate the sum of its element. So sum of 10 numbers we are trying to calculate. Or to be specific, 0 to 9. Right? We are trying to calculate the sum of numbers from 0 to 9. So this is what is happening. The only thing is, the moment you write this directive, number of threads in parallel are going to be created and they all are going to use this shared variable. A is equals to S plus A of I. Right? That is the problem. So this is the expected output. But in actual, this is what happens. We have run the same program multiple times. One time it's reporting 29, then 21, then 45, 45, 45, then 43. The result is not consistent. Right? That means again that shared variable. Whosoever thread is getting the opportunity is changing its value. That's why it's coming. So, what is the solution? The solution is to implement the concept of mutual exclusion. And we can do that with the help of this additional pragma. Hash pragma om critical. ये critical section आने वाला है. ये shared variable. This is the shared variable, and these are all the threads are going to make the use of this variable parallel.
Sorry to be vague. What happens if we use private or plus private in this case? Does it work?
I'll let you know to that point as well, because that we will discuss in the coming slides. Okay. The last private is straightforward. Okay, because the threads are individual. So whosoever is having its last value, because it's not considering the other values. Okay, only the thread which is being executed at last, whatever is its value, only that value is being reported. Private, all the values are going to be 0. And in first private, they are going to have their own local copy. They are not being shared with the other threads. But now it has to be shared. Okay, it has to be shared. So whatever is the critical section that can be protected by using this syntax, which is hash pragma on critical. So only one thread will be allowed to enter that critical section and will change its value. And that way it will be consistent. Okay, so this is the way.
All the threads are doing the same job because they are taking those
Except that S plus equals to A of I. See, this is very basic simple program, but in a for loop there can be number of things which we are doing. But at places there are some variables which are shared. Okay. But the problem over here is, knowingly or unknowingly, this is leading us to a serial program. Okay. So code is getting executed almost serially because of that portion. So we have a better solution, and that better solution is that for each and every thread we are having the local sum using this type which we just mentioned. So each and every thread will be having their local sum, and then at the end they will be reporting their value over here. So whatever value each and every thread have got over here, they are going to report over here, and it is going to calculate the final value. So this is how you can reduce the complexity by moving the critical section outside of the loop. So that way the memory access and other things are going to be limited or less in number, and that's where it is going to give you much better performance, or the better performance. Much better you will be getting with the help of reduction clause. We'll come to that. So again we are getting the output, but if you just do the performance test, let's say we have got n equals to that much, and you are running both the programs. Now you can see the performance. Comparing with the critical section when it was inside the for loop and when it has been kept outside the for loop. That is important. So number of access to the critical section has been reduced. Now we have got one more solution called as atomic. Okay, so that is also going to improve the efficiency. It is same thing. The only thing is that this time you are making the use of this atomic clause. Okay, this same. Now some variants are there. Reduction. So this is very important clause. So whenever you are making the use of for loop, more often you will come across this situation where you need to reduce on addition, subtraction, or some bitwise operator. So over here, rather than declaring the critical section in between, you can just make the use of this reduction clause. Like now, what changes we have done? We have added reduction clause for the variable x, and it has to reduce one operation plus. This way. So it will do the rest of the things. Again, it improves the efficiency by reducing the access to the critical section. That's how it improves the efficiency. So what you can do, you can just try the critical section, just increase the number of iterations. First execute the program with the small number, then increase the number. Then see the efficiency of critical. Okay. Then see the efficiency of the program which we have seen, where you are putting the critical section outside. Okay. Then see its efficiency with the help of this reduction clause. You will observe it. Okay. So these are the supported operators, and these are the opportunities which you guys can have in the field of HPC if you happen to come to this field. Then it can be HPC education, educator or training personnel, and then of course some research can also exploit some research ideas and all. So these are more or less some opportunities of HPC, and Government of India and CDEC is trying their level best to create the persons who are well aware of these technologies. Even if the students are able to have this understanding, if they go to CDEC, that I know what is HPC and I know how the curriculum is being done, then they will get the job. So with this, I am ending so that you can practice the things. Okay? Any question?
You suggest some source for going through this MBA because it's
J Queen book is there.
cheap.
Parallel programming. J Queen book is there for parallel programming with OpenMP with C language. You can just search it. I don't remember the exact, but parallel programming with J Queen with C. Parallel programming with C